Hello everyone, my name is Subho Mukherjee and I'm a senior researcher at Microsoft Research. Today I'm going to talk about resource efficient learning for large pre-trained models. This is a joint work with several researchers, interns and our internal collaborators. Our core mission is to bring intelligent AI experiences to every person and organization in this world, which means we need to build AI models for thousands of different tasks, domains and languages. However, it is quite difficult to custom build models for every domain and organization or language that we want to support. Even if we can afford the annotation cost, in many cases we cannot even see or annotate the data due to privacy and compliance reasons. In this regard, we have been working a lot on data efficient learning on how to scale AI to hundreds of different tasks and thousands of domains, but with only few limited examples or demonstrations. So first I'm going to talk a bit about self-training. For most of the practical tasks, you have some labeled data and large amounts of task-specific unlabeled data. Self-training as a semi-supervised learning has been quite effective in these settings, where you train the teacher model on some amount of labeled data. You apply the teacher model to the task-specific unlabeled data to collect the logits, which we call the augmented data. This augmented data can be used to train a student model. The teacher and student model share parameters and the training is repeated until convergence. However, a typical challenge with this setup is error propagation from the noisy pseudo labels. This equation shows the connection between self-training and entropy regularization. There are two loss terms here. The first one is the cross entropy loss over limited labeled data, and the second one is pseudo labeled loss over unlabeled data. Here we can do intelligent sample selection to prevent drift from the noisy pseudo labels. In recent times, we have been exploring a lot of techniques to improve the regularization and sample selection for few-shot self-training. We have been exploring several techniques like stochastic regularization to leverage uncertainty estimates of the underlying neural network, or leveraging the self-generated model explanations in the form of rationales to make it learn better, or even weak supervision in the form of domain-specific signals like regular expression and so on. So to give you a flavor of one such technique, let us consider this work where we use dropout distributions for stochastic regularization. So we sample several masked model weights given a pre-trained language model using dropout. Now given an unlabeled sample, you can pass these through each of these different masked models, collect the predictions, aggregate them, compute the mean and variance, which gives you an estimate of the uncertainty estimate of the neural network for the underlying sample. We can incorporate these estimates into the self-training framework to make it learn better. Furthermore, you can use these uncertainty estimates to do sample selection and leverage the teacher confidence so that the student can learn from confident teacher pseudo labels given by the samples with low variance. We applied this technique of uncertainty aware self-training to several text classification benchmark datasets, where our method, which is the one in yellow, is trained with only 30 labels for each class for each task, compared to BERT, which is trained on thousands of labels, and we note that we can perform within 3% of the fully supervised model. The previous technique applied to sentence classification tasks is a bit difficult to adapt to structured classification tasks like named entity recognition and slot tagging. In this work, we developed MetaST to bridge this gap. In MetaST, we leverage meta-learning to do reweighting for token-level pseudo-labels by injecting perturbations at the tokens and then doing consistency learning. We observe that our method MetaST can outperform several state-of-the-art methods with at least 10% improvement in the 10-shot setting, means that we can use only 10 labeled examples for each slot type. In all of the previous techniques, we use classic BERT-style fine-tuning. In recent times, prompt tuning has proven to be much more effective. In prompt tuning, we used the pre-trained language modeling head to do closest style sentence completion task, which bridges the gap between pre-training and fine-tuning. We incorporate this prompt tuning method into our previous MetaST framework, which we now call prompt ST, and we have several observations. We observed that a better teacher, since prompt tuning is better than classical fine-tuning in the low resource scenario, can lead to a better student, where we observe prompt ST to be better than MetaST. We also observe that self-training with unlabeled data can improve prompt tuning in the low resource scenarios. While doing the previous works, we noted that there is a lack of benchmark to evaluate true few-shot learning. Especially, there are several challenging questions on whether we should use a validation set, how many shots or labels should we use to compare the model performance, which tasks or metrics that we should use. In order to address all of these different questions, we developed the CLUES benchmark. CLUES stands for Constraint Language Understanding Evaluation Standard, in which we release several tasks and data sets, diverse scenarios like NER, reasoning, and classification, with human level performance evaluation. Here we observe that there is really a huge gap between human and machine performance for few-shot NLU, where humans really do well given only few demonstrative examples. Now let me shift gear and talk a bit about scalability. These pre-trained language models are huge in size, and it is difficult to use them in practice. So let me first talk a bit about adapters. So the core idea here is to use small tunable components or bottleneck layers in different layers of the neural network model. Now, instead of tuning the entire language model end to end, we will only tune these small adapter components. This makes it really efficient to deploy it for multiple tasks and scenarios where I need to keep only one copy of the original language model and several task-specific small adapter parameters. We use this idea with prompt ST, and we observe that we can keep the same performance as before, but now with prompt ST adapter, we are using only 4% tunable parameters compared to that before. Finally, adapters do not really resolve the inference latency challenge, as the model architecture is the same as before. In this work, we have been exploring knowledge distillation to self-train a student model given the hidden state representations and attention state transfer from the big teacher model. Using these techniques, we distilled several universal checkpoints with several magnitudes of faster inference compared to the big teacher model, but with matching performance. We released these checkpoints in the links below. Thanks a lot for your attention. You can refer to the following links for more information.